In this lecture, we're going to do 5 examples. So our first 2 examples are examples of working with the equation of a sphere. Then we'll graph a couple of equations, and then lastly, we will identify and graph 9x squared plus 4z squared minus 16z equals 20 in R3. Okay, let's start with this first example. We want to find the equation of the sphere centered at the point 3, -1, 2, and containing the point 4, 6, -2. Recall that the equation of a sphere is x minus a squared plus y minus b squared plus z minus c squared equals rho squared, where a, b, c are the coordinates of the center, and rho is the radius. So in this example, we already have the center, 3, -1, 2. We only need to find the radius. Okay, let's say this is the point P, and here's our sphere. Let's say the point Q is about here. Then the radius rho is the distance from P to Q. So to find rho, we're going to use the distance formula to compute the distance from P to Q. To compute that, we have the distance is going to be the square root of the difference between their x coordinates, so let's say 3 minus 4, that quantity squared, plus the difference between the y coordinates, so -1 and -6, that quantity squared, and then lastly 2 minus -2, the distance between their z coordinates, that quantity squared. So we get the square root of 1 plus 49 plus 16. So that's going to be the square root of 66. So the equation of this sphere is x minus 3 squared plus y minus -1, so I'll write y plus 1 squared, plus z minus 2 squared equals rho squared, so that's going to be equals 66. Okay, for our second example, I claimed the equation x squared minus 4x plus y squared plus z squared plus 10z equals 20 is a sphere. The way it's written, it doesn't look like the standard form of a sphere that we just had in the previous example, so we're going to take this equation, convert it into standard form, and then from that we can identify what the radius rho is. Okay, so if we look at this equation, we have a squared x term and a minus 4x. And then we just have y squared, we don't have any other terms with y. And then we have z squared plus 10z. So what we're going to do to take this equation as it's written and convert it into standard form is we're going to complete the square. To complete the square, what we're going to do is look at this coefficient in front of the x term. So that's minus 4. We want to divide that by 2 and then square it. So I'll write x squared minus 4x plus -4 divided by 2 squared. And then for the y term, there's nothing to do because we just have y squared. We don't have any first order terms in y. So plus y squared. And then for the z expressions, it's going to be the same deal. We'll take that coefficient of 10 divided by 2 and square it. So plus z squared plus 10z plus 10 divided by 2 squared. Now that's going to equal 20 plus the terms that we've added onto the left-hand side. So we've added 4 and 25. Now when I look at these x terms here, they factor perfectly into x minus 2 squared. And then again for the y terms, there's nothing to do, so plus y squared. And then similarly, the z terms also factor perfectly into z plus 5 squared. You can always check what you've done here by just expanding those terms on the left-hand side, squaring out the x minus 2 squared and the z plus 5 squared, and see if you get back what you started with. Then over on the right-hand side, this equals 49. And now we've actually converted this equation into the traditional form for a sphere. We recognize that the center of the sphere is 2, 0, -5. and the radius of the sphere is the square root of 49, so it's 7. So I went through completing the square here kind of quickly. I didn't explain the general methodology for how to complete the square. We're going to have one more example of completing the square in this lecture. But if this is unfamiliar to you, if you haven't done this in a while, you may want to review this on your own. Previously, we saw how the equation x squared plus y squared equals 1 gave us a circular cylinder in R3, and we were able to figure that out by realizing that we had no constraint on the z-coordinate. So if we could understand the shape as it pertained to x and y, then we could essentially just stretch it along the z-axis in order to get that cylinder. Let's look at a couple similar examples. So let's graph the equation z equals 3 minus y, first in R2, where really here, I don't want to be in the xz plane, I want to be in the yz plane. Let me fix that. So we'll start really by graphing z equals 3 minus y in the yz plane. Given that x is arbitrary in this equation, meaning we don't have any constraint on x, we could choose any value of x we like. So once we understand what z equals 3 minus y looks like in the yz plane, we can go over to R3 and sketch it in xyz space. Okay, so in the yz plane, z equals 3 minus y is a straight line with slope -1 and z-intercept of 3. So let's say this is 3, and we have a slope of -1. Okay, so here we have the positive y-axis and the positive z-axis. In R3, we recognize those portions of the graph as here and here. So here's the positive y-axis and the positive z-axis. If we work in the yz plane as a subset of R3, in other words, if we let x equal 0, then z equals 3 minus y is going to give us the same line that we just saw. So we'll pass through the point 0, 3, 0 and the point 0, 0, 3. So here's a portion of the graph z equals 3 minus y in R3. This is the portion that occurs in the yz plane when x is 0. But x doesn't appear in this equation. We have no constraint on x. So we could also let x equal 1. So I can essentially translate this line we drew down the x-axis. But we can do that for any value of x, and also negative values of x to go in the other direction. And what we end up sketching is a plane. This plane, of course, continues up and down and left and right. Okay, so that's probably the best picture I can draw of the equation z equals 3 minus y in R3. Let's look at a similar example. So let's graph y equals x squared in R2, and then we'll move it over to R3. Okay, so starting in the xy plane, we know that y equals x squared is the parabola that looks like this. So let's sketch what this would look like in R3. I want to call your attention to how to kind of rotate the x and y axes here from the picture on the left to the picture on the right. So you kind of have to twist your head and look from above. The parabola y equals x squared in the xy plane in R3 would open up like this. Okay, so that's the graph of y equals x squared in the plane z equals 0. But z is arbitrary here. We don't have any constraints on z. So we could take this parabola and kind of lift it up to positive z values and push it down to negative z values. And what we'd end up with is not what you might traditionally call a cylinder, but it's so similar to the circular cylinder that we saw before that we would call this a parabolic cylinder. And of course, as usual, we understand that this continues up the z-axis and down the z-axis, and then also continues to grow outwards for increasingly positive y values. Okay, let's finish this lesson by identifying and graphing the set of points in R3 that make the equation 9x squared plus 4z squared minus 16z equals 20 true. So when we look at this equation, we see 9x squared but no other terms with x. We don't have any terms with y. And then we have 4z squared minus 16z for the z-coordinate. So since we have a quadratic term for z and a degree 1 term for z, we want to complete the square. Okay, so I'll write 9x squared, no y terms, And then for these z terms, the first thing we need to do is actually factor out the coefficient of 4 in front of both of these terms, because when you complete the square, you want your quadratic term to have coefficient 1. So this will be 4 times z squared minus 4z, all equals 20. Now we'll complete the square with the z squared minus 4z. So I'll take that coefficient of negative 4, divide it by 2, and square it. So we get 9x squared plus 4 times z squared minus 4z plus negative 4 divided by 2 squared equals 20 plus, and then let's see, what have I actually brought onto the left-hand side of the equation that's new? We have negative 2 squared is 4, but then that's actually going to be multiplied by this 4 out here. So 4 times negative 4 divided by 2 squared. Okay, so now we have 9x squared plus 4 times z squared minus 4z plus 4 equals 20 plus 16. Okay, the z squared minus 4z plus 4 factors, so let me rewrite this as 9x squared plus 4 times z minus 2 squared, and then 36 on the right-hand side. This equation is an ellipse with respect to x and z. And then of course there's no constraint on y because it doesn't make an appearance in the equation. You could put this in the more standard form for an ellipse where we divide both sides by 36 to have 1 on the right-hand side. If I do that, then I would write this as x squared divided by 4 plus z minus 2 squared divided by 9 equals 1. Okay, let's work in the xz plane. And then once we've established what the ellipse looks like in the xz plane, we'll stretch it along the y-axis to create an elliptical cylinder. Okay, the center for this ellipse in the xz plane is 0, 2. So that's happening there. You have to be careful whenever you're thinking in the xz plane, because if I just sketch the xz plane at the top, then notice this is the positive part of the x-axis and this is the positive part of the z-axis, then it kind of flips when you move over to R3. So we've got here and here. So you have to look at the xz plane from a different angle. Okay, for this ellipse, the major axis is the vertical axis with respect to z, and the semi-major axis length is the square root of 9, which is 3. Okay, so we go up 3 to about here, that's the top of the ellipse, and then down 3, 1, 2, to about here. That's the bottom of the ellipse in the xz plane. And then the minor axis is parallel to the x-axis, and the semi-minor length is 2, the square root of 4. So we're going to have to go like over 2, over 2. A little bit hard to sketch this ellipse in R3, but it's going to look sort of like this. Okay, so that's our ellipse in the xz plane. Now we imagine stretching that ellipse along the y-axis because y is arbitrary here. We don't have any constraint on y in this equation. All we know is that the x and z coordinates, if you just look at how they behave, they have to live on this ellipse. And in the usual way, this ellipse stretches the length of the y-axis. So I've only drawn a piece of it.